This model shows a nice example of vortex shedding downstream from this circular rod in a two-dimensional flow. And right here we see the pressure or the flow distribution in these contours. And we can get a nice video of this if we go here to the player and we run the video, and we can see how this flow evolves with time. If we grab this slider and let's see, let's stop it, we can go back here. This is right here the startup of the flow, and then it had some kind of erratic patterns, but now the flow develops into this regular. You can see it's kind of oscillating here spatially, and we know that the pressure is oscillating right here in the vicinity of this obstruction. Okay, so that's what the pressure looks like. One thing that's quite interesting is what the flow field looks like. And so one way that we can do this is to use particle tracing. And what I did was to go to this plot that shows the velocity and go here to more plots. And then I've got options down here, particle tracing with mass and without mass. And so let's just look at particle tracing without mass. This would just be particles that are, say, attached to the water molecules. So it's not actually a particle per se within the flow. Or it could be a particle per se, but it just has the same mass and the same behavior as a water molecule. And so we're really just following the water molecules along. And when we do that, we need to specify some starting points and some starting times. So the way that I set this up, let's go back to the, let's just turn this back in time. And I think actually that's good enough. Let's plot that. So there's the pressure field after that many seconds. And I started the, I'm going to release these particles after 3.6 seconds. And I did that because it takes that long for these vortex streets to get stabilized. And I set this up with two of these, and this one releases these particles over this range from 0.1 to 0.2 in Y. So that's right there to right there. And I changed these to make them red, and I did that right here under coloring and style, right there. So they're red points, and they're going to be connected by a line as the points move through the model. What I'm going to do too is I'm going to turn off this color flood of the velocity. So then I just have this white background. That'll make the points and their trajectories easier to see. So I've got the red points in here, and then I've got this one here. These are some magenta points, and I have those starting at Y from 0.2 to 0.3. So if I switch back and back, notice right there. So those numbers shift, and the color right here changes, and also, yeah, I guess these points are green, and the line that they're going to follow, or that will follow them, is magenta. And there I have a couple of options here. Instead, the previous one was a line. This is a tube, and a tube we can change the width of it, or the thickness of the line. So here's what you get. We're releasing the particles at a time of 3.6. So at this time, 3.54, there's nothing has happened. We haven't released the particles yet. But if we go here, 3.8 seconds, the particles have been released, and there's what they look like. So the velocity is faster here than here, and you can see those particles. They're all released at the same time, but some of them are out and heading out ahead of each other. But we can see a very regular flow right here. But let's go ahead to 4 seconds, and now we see kind of a surprising thing, because We have these particles. There are the same number of particles on the top and bottom, and they're released symmetrically, but now we can see that the particles are in fact not symmetrically distributed. Some of these red particles are getting out ahead of the green particles, and their pattern is different. So that's kind of interesting. And that's a consequence of this complicated flow pattern that evolves behind this obstruction. So let's go another 2/10 of a second, and we see, boy, these red particles are really getting out ahead in quite a long way. The greens are kind of bunched together. These guys are getting way out ahead, and some of these, quite a few of these, I guess 4 of these red guys are are going to be getting trapped in this little vortex behind the obstruction. And this red one, this looks like this guy just collided with the wall, and he's kind of stuck there. So as the flow evolves, what we get is some particles kind of caught in this tangle of flow behind the obstruction, and these red guys are headed out, and we have quite a big cluster of the green particles. And look at this red guy. He's shooting all the way across the flow, and is even further towards the wall than the green ones that started out on this side. So very interesting result of this complicated flow pattern, and we see more of the same now as we march through time. This flow is clearly getting quite well mixed. So let's go a little bit further. This gives us just a very nice opportunity to see the trajectories of these points through the flow field. We can see this tangle of trajectories where we have a good bit of mixing, and then this oscillatory, or this kind of a wavy flow here downstream from this obstruction. So this looks pretty interesting when we see this video that allows us to look at it in real time. So we have to reset this from the last flow that had the velocities as a background. So we'll do that, and then we'll zoom in a little bit more here, and come on. Well, that's not so good. Well, so we can see these particles evolving and moving through the flow field and getting mixed. And so if we're interested, for example, in reactions and chemical reactions, then we're going to be very interested in how components that start out separated in a flow can become mixed together so they can interact and undergo chemical reactions. And we can see with this particle tracing analysis one way that we could think about getting at that kind of mixing information. We can also see that this very simple analysis with this circle in the flow causes a very complicated flow pattern and a lot of mixing.